טוב, בוקר טוב. Morning. So just a small reminder, we are started to talk about decision making, Bayesian decision, in the special case where the world has only two states, omega 1 or omega 2, omega 0 is omega 1. We get a sample xn out of one of the distribution where I can be either 1 or 0. And so this is what we will call later on observations, or we call already observations. So this is giving us this random variable xn. But notice that it may come from two different worlds, two different states of the world. And in this case, and we want to make an action. Leave some space here for something. We want to take an action eventually, which was in our case decide if the world is in omega 0 or in omega 1. Make a decision. So this action states A1 is decide omega 1, A0 is decide omega 0, and A or alpha, whatever. I want to keep the alpha for the error, so let's move to A action. And A1 decide omega 1, which in the case of hypothesis tested is called the null hypothesis and the alternative hypothesis. These are just different names for the same things. And we actually noticed something interesting, and I want to point out, that we can make the decision in an optimal way, at least in the base optimal way, or in the minimum error, minimum expected error of both types, if from only one function, very simple function of the sample. In some sense, we can take this n-dimensional vector, which can be huge in terms of complexity. Imagine n real numbers or something like this, and actually calculate one function that I want to denote by LR because it's a bit confusing. Likelihood ratio, because we use L for too many different things. So likelihood ratio, where this likelihood ratio was in some sense a compression, if you want, mapping of this high-dimensional vector, n-dimensional space, into one number, one real number. So this likelihood ratio of the sample was the ratio of the probability of the sample in the first state of the world divided by the probability of the sample in the alternative, or in the second state. Okay? So this is, in some sense, something which we later on will call, it's a special case of something we're going to call later on a statistic. So this term statistic is a bit confusing, but it's function of the sample that is going to map, it's a function from the sample, which is not necessarily IID. I mean, we don't have to assume that it's IID at this point, into the reals or into some high dimensionals. In general, it can be some dimensionality, not necessarily R1, which in a sense, so functions like this are called statistics. A function like this is a statistic of the sample that in some interesting way capture everything we're interested in. So we actually want to call this particular property of statistics, we call them sufficient statistics, because they're sufficient for making the decision. Okay. So this is something which I'll come back later on is going to play an important role in this course, this concept. So this is a sufficient statistics. Statistic in this case. So it's a method that somehow compresses the information. And then from this sufficient statistic, we actually make a decision. And the decision the decision rule that we found to be optimal is a threshold comparing this likelihood ratio, or if you want any monotonic function of it, like the log likelihood ratio, to a threshold. Okay? So for example, in this case, this was compare the likelihood ratio of the sample to a threshold, and I denoted it by this. This theta is going to cause us problems later on because we're going to denote theta by parameters of distribution. So. But at this point, you know what I mean. Again, notations are always a problem. I mean, you realize that you introduce one notation and then you use the same symbol for another thing, just because this is the literature. But then you get into conflicts. Anyway. So this is some sort of a threshold, and this was the optimal decision. And it was optimal. We showed it in essentially one or two different ways. One was for the Bayesian optimal risk in the sense of error, and it was also independently proved through the Neyman-Pearson lemma in statistics, but actually we proved the Neyman-Pearson lemma from the Bayesian optimal decision. You can actually, with a very small change in the proof I showed you using the prior, you can just you don't have to say anything about priors. Just compare it to a threshold. This is the best proof and the best possible test that you can do. So this is in the context of hypothesis testing, as we call it. This is the optimal test. So hypothesis testing is really the fundamental. It is binary decision. I mean, decide if to go left or to go right, or to take an umbrella or not take an umbrella, or to decide between two alternatives. Is really this fundamental, and once we understand this, we'll eventually generalize it to much more complicated scenarios, many decisions, changing world, changing cost functions, whatever you want, and eventually this will be the foundation. I mean, if you understand binary decisions, you really understand something fundamental about this game of behaving in the world, if you want. So this is, in the context of hypothesis testing, this is called the likelihood ratio test. And of course, in optimal here, so this is optimal decision. Optimal in the Bayes optimal sense. Which means that we actually have a cost function that we minimize its expectation. And so the cost function in this case was chosen such that the expected error, the weighted sum of the two types of errors is minimized. Okay? Any questions about it? So if you notice, I'm actually, in this summary, I always introduce something new, but it's all right. So, yes?
The dimension D is sort of some lower dimension?
It's okay. That's a very good question. At this point, I don't want to say anything about it. I just want to say that the statistic can be in general a vector? It's a good question. What is this D? It's the number. It's the number of interesting. Maybe you can't summarize all the information in one number. Although in real numbers you can play all sorts of tricks. You can compress n-dimensional vectors into one number simply because there's a one-to-one mapping from RD to R. But this is not what we mean by good mappings. It's usually not very continuous and not very nicely behaved. Okay, so it's a tricky question, and we'll come back to it. So, but in general, this can be n-dimensional, d-dimensional. Not n is so far reserved for us for the sample size. Okay, just to more or less be consistent. More questions? So this is clear. So I hope that by now you, after doing the exercise, you should make the whole thing much more concrete and much more understood. Without the exercise, you can't really understand it. I mean, there's no way. Okay, so this is something which in general we are going to call batch learning. I mean, we take a sample of size n. This is all the data we get, and we make the best we can with it. Decide based on this. This is batch learning. But we started to talk about something which we later on call online learning or sequential learning, where sequential in this case means that, okay, maybe we don't get the samples at once. Maybe we have the choice of sampling more and more and more, and for each sample, we want to decide. And if we are not sure, or our probabilities of error are not sufficiently well guaranteed, continue to sample. Okay, so we actually want to take this from batch learning, or batch decision, if you want, to online. Online or sequential. Sequential learning. And what do I mean by sequential learning? And I said exactly, I want to sample as long as necessary to make sure that I make the right decision. And think about it, this is the way we usually behave in the world. I mean, we don't just take data and decide. Sometimes we do, we have no choice. But in most cases, we actually have access to the world or to the source, as we'll call it later on, of the information. And we query, we ask more. Okay? And we want to ask enough. And so we want to turn it into online learning or online decision. And in our case, it's actually very simple. It's particularly simple, by the way, if the sample is indeed IID, then this is simply a product of IID numbers, which are these likelihood ratios. And as a product of IID numbers, we saw last time that it behaves nicely asymptotically. But at this point, I actually want to prove a much more general theorem, even without assuming that it's an IID. We don't need this assumption for proving this theorem. So in order to make it into sequential decision, essentially what we're going to talk about is something which in the literature is called sequential probability ratio test. Or SPOT. And it's, as I said already, it's a very important practical tool for making decisions online. And this is attributed to Wald from 1942, that actually opened the door for many, many new things since then. And actually, as I said, I mean, it's really the origin of what we now call in learning theory online learning. So what is this theorem? So I already said that at least in the case where these are IIDs, we actually showed something quite interesting, that the log likelihood ratio, the log of this ratio of probabilities, looks like a sum of IID numbers, and therefore, by the weak law of large numbers, goes to n times the expectation. And we actually talked about this expectation and call it, and show that it has some nice properties. I mean, the log likelihood ratio in one of the two states go to a number which was n times the Kolmogorov, the Kullback-Leibler divergence between these two things. Kolmogorov will come later. So much later. So you actually saw a little bit intuitively that if we look at the log of this likelihood ratio, so I think I want to save time, so I write it like this. If in the IID case, which is it's not necessary for what I'm going to say, this is going to behave like a random walk. For the physicists, or those who saw it before, it's some sort of a random walk. So when I see a sample which is more likely in one hypothesis, let's say omega 0, then this ratio is going to be greater than 1, which means that the log of it is going to be positive. And then I'm going to make a positive random step. And if I see something which has more probability in omega 1, this log ratio is going to be negative. So this is going to be a sum of positive and negative numbers. But on average, it's going to increase linearly with n, where the slope is precisely what I call the Kulpa-Fleiberg divergence between the two hypotheses, or decrease if I'm in alternative hypothesis with a negative slope of the alternative Kulpa-Fleiberg divergence. Okay, this we already saw. It's and of course, what the intuition is telling us is that maybe we should split this likelihood ratio test into actually two thresholds. Put some number here, which we would like to call A, or log A actually, and some other number here, which we are going to call log B. And this is going to be a positive number, and this is going to be a negative number in general, unless there's some offset of the 0 here due to the prior, which I'm not going to talk about at this point. But essentially, make the decision only when you cross one of these two numbers. And if you're still in between the numbers, continue sampling. So that's the idea. It's a very simple idea. It turns out to be, as I said, but what is really interesting is that we can actually determine these two thresholds, A and B, without knowing anything about the distribution, just based on the probabilities of error, alpha and beta. It's not exactly the thresholds, they're going to bounce to the thresholds. And this is really what turned the whole thing very, 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 very significant and very practical, because you can easily say what two thresholds should be in order to get alpha and beta error, given alpha and beta, without any assumption about the probabilities, which makes this sufficient statistic even more impressive, because it's in some sense universal sufficient statistic. It's independent for anything that any assumption about the probability distribution, or it's a distribution independent statistic. Okay, so the theorem we want to formulate and prove the following. So let me make sure that I don't. So given the likelihood ratio test that I just defined it, I just want to make sure that when you formulate theorems, you have to make sure that all the quantifiers are right. So the theorem, where is it? It's going in the wrong direction. Okay, so the theorem is given P of x n in this state, and P of xn in the other state, for any alpha and beta greater than 0 and less than 1/2. Especially in the book, it says less than 1, but you really don't want them to be larger than 1/2. Otherwise, you get all sorts of funny things there. So if the probability of error is larger than 1/2, essentially it tells us we are better off without making the test, because a random choice will do better. So we assume that the probabilities of error are less than 1/2. Um, so for any alpha and beta, the test defined by this. If the likelihood ratio, or if P of xn, no, I'll write it. I already defined the likelihood ratio, it's right here. So if the likelihood ratio of xn is greater than A, okay, this is actually for any alpha, beta, and for any A greater than 1 greater than B. Okay? Two real numbers, one greater than 1, one less than 1. And this is actually greater than 0. So any two thresholds like this, okay? Oh, no, forget it. For any likelihood ratio in which this is greater than 1 minus alpha over beta, beside omega 0. And if the likelihood ratio of xn is less than alpha over 1 minus beta, decide omega 1. Now the ratio was omega 0 over omega 1, so this is going to be greater than 1 on average if I'm in omega 0, and this is going to be less than something, less than 1 on average if I'm in omega 1. This is, of course, assuming that I can actually make the decision, which means that these probabilities are not identical. If they are identical all the time, then nothing can happen. I mean, I don't have information. Okay? And what in between? So if this likelihood ratio is between A and B, continue the test. Okay? Is this clear? So this is the test. And the theorem is this test, which is defined by this, has probabilities of error errors, which we call alpha prime and beta prime, that obey that alpha prime plus beta prime is less than alpha plus beta. Yes?
I'm not sure why the middle condition is mutually exclusive with the others.
Yeah, A and B, I'm sorry, I had to say the two numbers here. One alpha minus beta, and 1 minus alpha over beta. Forget about A and B for a second. I'll come back to it. This is simpler. Okay? So this is what we want to prove. So that this particular test will have errors that's such that the sum of errors is smaller than the sum of the errors of alpha and beta to be predetermined. Okay? So given any alpha or beta, take these two thresholds. These are these two numbers that I had before. They will guarantee and do this sequential test. Once you decide, the probability of error is going to be the sum of the probabilities of error of this particular test are going to be less than the sum of alpha and beta. No. Unfortunately, I mean, this is written wrongly in the book. It's a small mistake. It's not a big mistake. I'll show you. It's not really a big deal. I'll show you why it's not a big deal. So just notice. So this is the theorem, yeah? This is what we want to prove. Notice that if the sum of errors is not greater than the sum of errors, then the ROC curves of this test. So imagine ROC curve is 1 minus beta over alpha with respect to alpha, okay? So it's power versus significance. So we know that this is some sort of a monotonic curve. This is going from 0 to 1 to 0 to 1. And we know that it's always, well, we don't even know that it's always above the diagonal, but maybe we do. In our case, we assume it's greater than 0. But it's usually the ROC curves, as I suppose Noga already showed you, but if not, she will show it tomorrow. It's a well-defined function in the sense that that's really the best thing you can do with a given test. And actually, in many practical applications, we really quantify this by the area under the curve. You're going to see this in many papers to actually do tests like this. So the area under the curve is the quality of the test in some sense. And when the perfect test would be what? That actually fills all the square. Which means that once you have an error, I mean, for any error, you get perfect beta, so you can do 0 error on this. So the perfect, so anything which is better than this test should have a higher line. So actually, it's not, it's easy to see that if this is true, then the test I'm going to do with this threshold is actually having a higher ROC curve. It's going to have, so if the two alphas are equal, the betas should be smaller. And if the two betas are equal, the alphas should be smaller. That's what it means. So the curve that I get with this test is guaranteed to be not lower, somehow above. So this test is actually a better test. So for the same alpha, the beta prime, this is the prime curve, and this is the curve that I wanted. So the prime curve, the one I do with this test, is actually going to be above the ROC curve. So in that sense, it's a better test. I know that Amir said some other things, but that's what we really care about, the ROC curve. Yeah?
Can I take these alpha prime and beta prime and put them back in the test and run the test again to get an alpha, new alpha and beta, which is better?
Well, yeah, in principle, this is for any alpha and beta. Yeah, so you can improve the test by extending the sample size. In general, yes. So essentially what we're actually going to show, if I look at this, look at this picture, actually two thresholds here. Now I don't have too much space here, but I'll draw it anyway. So if this is the test, essentially what we're going to show is that this number, log of 1 minus alpha over beta, and these numbers, log of alpha over 1 minus beta, are greater than log A and log B, that will achieve alpha and beta. Which means that I'm actually making this is what I'm going to show you. So which means that I'm actually putting through two thresholds which are greater than those thresholds that I really need. So essentially what we're going to prove, and this is the main part of the proof, that A that achieves alpha and beta is less than 1 minus alpha over beta. And B that is needed for the same test is larger than alpha over 1 minus beta. So this will make the new test, this is the prime test if you want, more severe. I mean, I ask more, because the thresholds are further away, which will eventually guarantee that indeed alpha prime plus beta prime is less than alpha plus beta. Those who actually want alpha prime to be less than alpha and beta prime to be less than beta, think about it. It's not that easy to, you don't really know what you mean by that. We can't prove that. But we can prove that the ROC curve is better. Okay? Yes?
In this intuition about why both borders depend on both errors decide the final result, I mean, how come that the border, that the upper border A depend on
I think that the proof is going to convince you. It just comes out from the proof, okay? You'll see it immediately. Instead of trying to explain it now, wait to see the proof. Okay, so we want to prove this theorem. And you see that if you actually can achieve a better ROC curve, we consider it a better test in general. It's much better. Okay. So the theorem is really very simple. Although it looks a little complicated, it's really very simple. And actually, it's typical to many proofs in learning theory. So I think we're actually going to use this idea, maybe, if I get to it, in at least 2 other places in the course. And this idea is called the composition of the sample space somehow. So the proof is the following. Okay, so what happens here? I mean, I can actually divide my sample space into regions, which I want them to be disjoint, such that for each one of them I make precisely the decision after n samples. So I'm going to find, so let's define something which I call Cn. This is the same notation as in the book. So Cn is going to be the sample. This is, by the way, not covered by Amir notes. It used to be lecture 2, but somehow he decided to take it out. So this is in the Hebrew book, and maybe we'll get some English summary as well at some point. Never mind. So what is Cn? I define it to be as all the samples such that we precisely cross the line, the threshold A. So let's call it, given at this point, let's call them 2 thresholds just to make it simple. A greater than 1, greater than B, greater than 0. Okay, so I precisely cross the threshold A after n steps. Well, no, actually, I cross the threshold B. So which means decide omega 1 after, this is again something I can always decide omega 1. I just want to be consistent with the notation in the book, not to confuse you. It's really very confusing. So decide omega 1 after exactly n step, n samples. Which means what? So this is all the samples where the likelihood ratio is between B and A, not L. For all L's between 1 and n minus 1, which means I didn't cross the line until then, okay? And then it's exactly the likelihood ratio of xn is exactly smaller than B for n. Yeah. Okay? So this is what it means. So which means that up to n, again in this picture that I should keep here all the time, up to n I didn't cross the line. This was the first time this particular n, this is the sample size, this particular n was the first time I crossed the line. So until then I was wandering in between. Okay? So the first time I crossed this line actually, this is the B. So this is what I call Cn. So Cn for every integer n is the set of samples that will cross the line exactly after n steps. Okay? And similarly, I defined Dn, which are precisely the complement. And so not really complement, they're different sets. So decide omega 1, instead of decide omega 1, decide omega 0, which means LR XL is going to be between B and A. For L between 1 and n, minus 1. But LR is going to be precisely for the first time for xn greater than A. Okay? So this is the probability that I eventually decide omega 1 after n steps. This is the probability that I decide omega 0 after n steps, n samples. Okay? Is this clear? This is the key construction of the proof. Once you understand this, everything is simple. Yes?
Actually, the set of orders.
Well, not necessarily order. Well, you're right. Yeah. Since I didn't say that it's the IIDs, I don't want to make this assumption at this point. I don't need to. You're right. It's order sample. If the IID, I don't care about the order. Okay? So there can be dependencies. So it's a good point. It's an ordered set. Actually, usually when we say sample of size n, we almost implicitly assume that it's IID. In this case, I actually talk about the vector. And you're right. You may get the most important sample at the end or the beginning, so it may depends where. For example, if you do your test between English and French, well, what is it, English and Spanish? English and French. So you'll see, maybe you see a letter, I don't know, E is very common in English, less common in French, so it's very informative about English. U is the opposite, I think. So, or I don't know, if you see Q is much more common in English and in French and in English, but for example, if you see the pair QU, you can almost be, or Q without U after it is almost certainly not English. So there are many things that are highly informative. So the samples can be, of course, the order of the sample matters in this case. Okay. So now, notice is always important. Notice that the Cn are disjoint, are mutually disjoint. They are not exhaustive, by the way. It's also another mistake in the book. And so the Ci intersection Cj is null if I is not equal j. And similarly for the Dn. Di dj is also. So why is this? They're mutually disjoint. Yeah. If you cross it at n, I defined it exactly at n, but not before n. I don't care what happens after. I don't continue the test. So it's exactly at n, which means that if it crossed at n equals 3, it belongs to C3 and not to C2 and not to C4. Okay. All right. So it's a real disjoint partition of the sample space. Of course, in principle, there may be other regions. I mean, in principle, you can continue this test forever. I mean, there may be some region where you never converge. There may be samples which will take you, for example, if it's not English or French, it's something else, with some mixture of the two, and nobody told you that. You may fluctuate between these two samples forever. So there may be something, of course, in my case, the world was only two states, so it's either one or the other. But, you know, so in principle, the union of the D's and the C's is the whole omega. It's the whole sample. It's exhaustive. But, you know, there may be some other region where you simply fluctuate forever. So forget it. I don't want to say it to assume this. So now it's really very easy to see that the probability of deciding omega 1 is what? Is the probability of the union over all ends of Cn's. Okay? The probability is that I decide omega 1 at one point. Okay? This is simply the probability of this union because, okay, I will cross at one point the threshold, the right threshold, the lower threshold in this case. And this is what? Since they are disjoint, what is this? It's simply the sum. The sum of the probabilities of Cn's. And I don't even have to tell you what these are. Formally, I can write it as an integral over the samples in this region, but it's enough for me to write it like this. And of course, the probability of deciding omega 0 is simply the probability of the union of the D's, which is the sum. Okay. So this is my main construction for this proof. And now a few very simple consequences. So notice. So how can the whole point of this construction is to relate these two constants, alpha and A and B, to the error probabilities, alpha and beta. If you can do that, then essentially we have what we want. You see immediately. So we want to see what is the connection between the thresholds A and B, which at this point were arbitrary, and the probability of errors. So I defined this in the formulation of the problem. I actually explicitly wrote. This is why I was hesitating here. I could write here A and here B, but I actually put this particular relationship between A and B already to the errors to really put the punchline of the theorem. That the fact that I can actually take these thresholds to be only functions of the errors. But now I want to prove it. So now I have these A and B's, which are any two thresholds like this, and I want actually to relate these thresholds to their errors. Okay. So for any two thresholds, A greater than 1 greater than B, I'm going to have some interval in between where this can fluctuate. Okay. And I just want to say, okay, what are the errors with these two thresholds? Okay, is this clear? This is really the only tricky part in this argument. So notice. So what is alpha? Probability, the first type error. It's the probability of. Sometimes it's called the false positive, false acceptance. Actually deciding omega 0 when I was actually in omega 1. Okay? Or the opposite. The opposite. So actually alpha is the probability of the union. Probability. So alpha in this case is simply the sum of the probability of Cn conditioned on omega 1 or 0. That's exactly where we. This is precisely where I'm always confused. Deciding the probability. It really doesn't matter. It's not important. I just want to make sure that I'm doing this right. Cn is the probability that we cross omega 1, so it's under. Yeah. Psi omega 1. Okay, agree? It's a probability that I decide that I.
According to your border, it's supposed to be the
Yeah, that's exactly why I decide omega 1 by mistake. Okay, you're right. Okay? Decide omega 1, this is the probability of decide omega 1 at when xn is actually coming from omega 0. Well, the word was. Okay. So this is alpha. And similarly, I can write that 1 minus beta. So what is 1 minus beta? Is the probability of true acceptance of omega, true rejection of omega 0. So it's again the sum over n goes from 1 to infinity of the probability of Cn. Yeah, Cn at omega 1. Okay? Yes? Yeah. It's false positive, as it's sometimes called. Yeah, so I know that I'm making a mistake in here. You know, okay, you're probably right, but since this is actually a mistake in the book, it really doesn't matter. I mean, you're absolutely right. Alpha is probability of false positive. Yeah, so you decide omega 0 wrongly. And actually, I wrote it the opposite. So it's there. Decide omega 0 where I was at. So yeah, you're right. Actually, I wrote it decide omega 1. You're right. I don't want to argue about it. It's just a matter of definition, which I'm always, and not the only one who's always confusing about it. Let's be consistent with what I write on the board. And I think you're right, but don't confuse me anymore. Okay, so 1 minus beta is this, okay? But this is really the important point. And so notice that, so this is the probability of correctly reject omega 0 or correctly accept omega 1, okay? This is what it is. So notice that these are probabilities of the same partitions, the same sets. And just to make sure that you understand, so this probability for any n of Cn, let's say, given omega 0, is simply what? So I can write it formally as an integral over all the set Cn of the samples xn given omega 0. For any omega, never mind, dxn. So this frightening integral is nothing but, okay, so we actually integrate or sum over all the possible samples which are in Cn, okay? That's what it means. I remember in previous years that people actually thought that they have to carry out this integral somehow. No, it's just a way of, this is what it means. I take the density of the samples and integrate it over the domain Cn. Okay, since the Cn's are disjoint sets, this is summing over all these layers of different decisions. Okay, so this is what it means. And similarly, same thing is true for Dn, but I replace Cn by Dn. I don't even have to write it now. Okay, so but notice that at Cn, what do I know about it? So at xn belongs to Cn. I know what? I know that the likelihood ratio was exactly less than b at n, okay? So at Cn, by the definition of Cn, the probability of xn in omega 0 divided by the probability of xn at omega 1 was what? Was less than b across the lower threshold. Exactly. This happens, which means what? Which means that the probability of xn at omega 0 is less than b times the probability of xn at omega 1. This is what it means. Okay? So here is the connection between the two arrows. So essentially what we know is that alpha, so I just combine these two things. So I know that I take the first line, so alpha, which is the sum, as written here, over n of the probability of Cn given omega 1, is for each term in this sum greater than b, the probability of Cn at omega 1. So it's less than b times the sum of the probabilities of Cn at omega 1. Okay, that's what I wrote here. Which is what? Which is b times 1 minus beta. This was the probability of 1 minus beta. So this is simply a consequence of these two things and what I wrote before. So what I get is the simple, nice relationship that b is what? So I get that b is greater than alpha over 1 minus beta. Okay? Notice that 1 minus beta is positive, so I can divide by it. Okay, so it's this is true, and in exactly the same way for the dn's, and you can complete it yourself. It's exactly the same idea. I just write the same for the dn's. Similarly, I get the opposite. I get that a is less than 1 minus alpha over b over beta. For exactly the same calculation, same argument for dn. Doing the same for dn. So I got this very nice. This is what I wanted. This is the main part of the theorem. Once I have this, I'm done. Essentially, what I showed you is that for any two thresholds, A and B, alpha over 1 minus beta is less than exactly what I wrote here. Alpha minus 1 over beta is below B. And 1 minus alpha over beta is above A. And this is also true if you take the logs. Okay? So these two, essentially what we just showed in a very simple way, actually. And actually, it's a slight generalization of the Neyman-Pearson lemma if you think about it. So this is log of 1 minus alpha over beta, and we showed that this is greater than log A. This is what this means. And we showed that log of alpha, here, log of alpha over 1 minus beta is smaller than log B. Okay? So essentially, what we just proved here is that these two numbers that depend only on alpha and beta are outside the thresholds that are needed to achieve alpha and beta. Okay? Okay, so this is it. Now to answer your question, who asked me now how can I continue it or whatever. So first of all, it's really a bit strange that both alpha and beta participate in the two thresholds. If you think about it, it's not that strange. And this is precisely why you get this eventually only the condition that alpha prime plus beta prime is less than alpha plus beta and not more than that, because both thresholds depend on the two errors. And I'm actually out of my time. So if you want, we can call this now log A prime, and this one log B prime. And now can continue. I mean, so what are the errors, the actual error of A prime and B prime? Using exactly the same argument, if you call them alpha prime and beta prime, what we actually showed is that their errors, alpha prime, for these two thresholds, alpha and beta, what can I write? So if you call these two A prime and B prime, so for the thresholds, A prime equal, what was it, 1 minus alpha over beta, and B prime equal alpha over 1 minus beta, the errors, we know that A prime is actually less than 1 minus alpha prime over beta prime, and B prime is actually greater than 1 minus alpha prime over 1 minus beta prime. We simply repeat the same argument for these two thresholds. Agree? I mean, I just wrote prime on the main result I just proved, but since A and B, since we know that A prime is greater than A and B prime is less than B, what we get from here is that this is less than 1 minus alpha prime over beta prime, and this was greater than 1 minus alpha over beta, and this is now greater than alpha prime over 1 minus beta prime, and this was less than. Sorry? Maybe I'm wrong with the signs here. Okay, I know that beta prime is less than beta. Which beta prime was, and alpha prime, alpha is less than, was equal by definition to alpha over 1 minus beta, which was less than B. So what we get out of here, This is also this. This is equals to 1 minus alpha over beta, which was greater than A. So what we get essentially these two inequalities. 1 minus alpha prime over beta prime is greater than 1 minus alpha over beta. And alpha prime over 1 minus beta prime is less than alpha over 1 minus beta. Now from this, it's an easy exercise. Show that, I am out of time, show that alpha prime plus beta prime is less than alpha plus beta. QED. You show. I mean, it's just multiply by the two, use the two inequalities and compare them. Okay? So this follows immediately. If you're not sure, just multiply this and then multiply this and arrange the terms. You get alpha prime beta plus beta prime alpha in both cases, and just compare them. So this is it. Okay, so this is really at the end of this saga. Usually this takes me an hour, and it takes an hour. So this is it. Now, just one more comment before we actually consume the break completely. Notice that neurons, I mean, we actually show that perceptrons can do hypothesis testing optimally in the Bayes sense, if and only if the inputs were IIDs. Now, neurons, as many of you should know, really integrate evidence. There's an integrate and fire a model of neurons. I mean, they really cross the threshold. There's an accumulated evidence. And actually, this reminds us very much of the way neurons integrate. So you can think about neurons as integrating data, accumulating the membrane potential, or any synapse that actually gets current inside, and eventually cross the threshold. So this is actually an excellent model for the way neurons actually make decisions. And some neuroscientists actually take it very seriously. I actually asked Noga to put on the webpage a paper by Michael Shedlon and Newsom, I think, that really make this analogy and really calculate properties of neurons based on this. Although they don't really refer to Wald, that's what they have in mind. And that's exactly why we believe neurons can make optimal decisions even sequentially. Okay, I'll stop here. Let's take a 10 minutes break and resume. I don't want to go over time next hour because Yoram is going to kill me if I do this. Okay. So ask all your questions now. כן. אז זה לא מתפרק לסכום. זה לא מתפרק למכפלה.
כל פעם ההתפלגות הזאת משתנה. אין סוף התפלגויות. שכל פעם שונות.
לא, זה לא משתנה.
לא, זה התפלגויות שונות.
אני לא הנחתי את זה. כל מה שאמרתי עד עכשיו לא תלוי בהנחה הזאת. צודק שאם זה לא IID, אז כל הסיפור נעשה הרבה יותר. אז אוקיי, אתה צודק לגמרי שאם זה לא IID, אני גם לא יודע שזה יעלה מונופולית. יכול להיות דברים מוזרים אחר כך. לא, בעלייה הזאת. אני לא יודע שיש פה לינארי. יכול להיות שזה יתקשר. כל הדברים מוזרים, אבל אני דיברתי עליו ולחצי הפעם שלה. כל מה שאמרתי בהוכחה הזאת נכון גם אם זה לא IID. צודק שבאופן מעשי אנחנו נניח IID עושה את הכי הרבה.
לא, ההנחה שזה הכל, שה-DN'ים וה-DN'ים, האיחוד על הכל, זה הכל.
לא, זה לא, אני אומר, אמרתי, יכול להיות שיש האיחוד של שני אלה או לא הכל, ויש עוד איזה סט שבו אתה ממשיך את הנפל הנפל.
אז אני כל פעם דוגם...
אתה עולה, יורד, אף פעם לא חושב כתוב. אבל זה אומר שאתה לא נמצא באף אחד משני העולמות האלה באמת, או שזה ספיות שלך מאוד ספיות, כן. יש ספיות מאוד מורכבות, זה ספיות, ואז אני לא מקבל את זה.
רציתי גם לשאול עוד שאלה לגבי האלפא טאג והבטא טאג.
כן.
אלפא טאג ובטא. אלפא טאג ובטא טאג זה הטעויות שאני מקבל כתוצאה מהמבחן הזה. ואלפא ובטא זה איזושהי בגלל תוצאה של מבחן תטא כלשהו?
לא, אני אמרתי ככה, אני אצפה לי אלפא ובטא. תקבע את הספים להיות הספים האלה. עכשיו אני אומר, להם יש שגיאה חדשה, אלפא פריים בטא פריים. זה השגיאה שאתה מקבל במבחן שהמסתכלים מצויים באלפא ובטא פריים.
עכשיו שאלה נכון אמרת לי ש-X משתנה מסוים מעל קו המדגם. המדגם הוא מגודל 2. אז אם X משתנה מסוים מעל מרחב המדגם, זאת אומרת X הוא גאוני אומגה.
לא, זה לא שזה אומגה 0 איחוד אומגה 1. וכשאני אמרתי אומגה 0 התכוונתי לקבוצה הזאת. עכשיו פה יש המון מצבים, כן, העולם נורא מסוגל. יכול להיות שראש הממשלה אמר משהו אחד בבוקר, יש לי נס גביר, כל מיני דברים מטורפים יכולים לקרות. אז באמת, יכול להיות שהמשתנה המקרה זה תלוי בהמון דברים שלא ראיתי גם. וזה נורא גדול.
אבל אני לא רוצה לסתבך בקבוצה הזאת או בקבוצה הזאת, זה לא תלוי בדברים אחרים שלא קשורים.
לא, אבל יכול להיות שבקבוצה הזאת שאתה דוגם ל-X, אני מקבל ערכים שונים מה-X הזה. ויתן לי כל מיני נקודות שונות בקבוצה. אז זה כל המהות, שאני לא הפרעתי את הסברה הזו, אמרתי שזה איכות של 2 נקודות, אבל בעצם זה איכות של המון נקודות.
הם אומרים בספר
הספר שלנו.
כן,
כאן שווה טעויות פשוט. אני לא מדבר על העברות מוסרית, ואני כמעט לא הסכמתי את השפיעו על זה. אבל
היית רוצה יש מקום אולי להוסיף
מה לסיכונים? כמעט הפסקתי לדבר עם גל צ'צ'יק. אני לא רוצה להגיד לכם יותר מדי. אני רוצה את זה, טוב שאני עושה את זה, אני חייב להגיד להשמתי שלא עברתי את זה. אבל יש המון טוב. זה בסדר.
בכל מקרה, מה שאתה חושב שאתה בספר, או הם, זה שיש שני...
האקטורות היא לא קרדינלית, בעצם זה בסדר יותר אוקיי.
אז אומרים שיש הבדל בין בהיפותזיס טסטינג, אם העולם שלי הוא באמת אומגה 0 איחוד אומגה 1, או אם הוא ממש יחידון...
נכון, יש הבדל, כי אז אתה מגדיר את ההסתברות של הפילוג הזה לכל אחד מהאומגות, אתה בדרך כלל לא רוצה לעשות את זה, הסתברות השגיאה לכל אחד מהאומגות, בדרך כלל לוקחים סופרים או כל מיני דברים עשו לזה.
הם עושים את הניתוח...
זה מסתבך מאוד את הארגומנט. בשאלה שלך אתה צודק, כן, אומגה מפניתו מרחב גדול, רצף, יותר מרצף, מה שאתה רוצה? שאני יוצא מיפוי עליו, והמשתנה האמיתי יכול לקבל הרבה מאוד ערכים. בסופו של דבר מעניין אותי החלוקה הפרטית שלנו לשני מצבים, ואתה שמח לו. זאת אומרת, אם אתה מרגיש את הדמות האלה, אני לא חושב שכולם מרגישים את זה.
לא, אבל זה
מהות. לא, אבל זה לא דבר כזה קשה.
שקר, רגע.
לא, זה לא שקר, רגע. כשאני אומר כשאני אומר שפי, זה דבר הזה, הוא משנה ממשי, למרות שיש רק מצב אחד, אבל יש איזשהו פילוג, למשל גרסי, שבמצב הזה הוא כאן, במצב הזה הוא כאן.
אני לא מבין עדיין, איך אתה אומר ש-X מתפלג אם אני באומגה 0. זאת אומרת, לכל הקבוצה הזאת, ה-X מתפלג ככה. נכון? אם אני בתוך הקבוצה הזאת...
בממוצע, לפני כל, מה שאתה חושב זה למצא עכשיו על כל המצבים בקבוצה הזו, לסכם עליהם, ואז אתה תקבל שהפעילות הנורמלית זה בתחום של הרבה מאוד דברים משתיים, וייתן לך מפת דבר מרכזי, ייתן לך כל מיני נחמדים בדרך, אבל בעיקרון כן, זה ההתפלגות הממוצעת של איזשהו אומגה שתגום במחשב. זה שקר, אבל זה שקר שעושים אותו כל הזמן, לא הייתי קורא לשקר גס. אי דיוק מוסכם על כולם. הייתי לא מדויק. בטא, 1 מינוס בטא זה החלטה שגויה, קבלה שגויה של מה שנקרא false positive.
לא, בטא.
סליחה, אלפא זה false negative, ובטא זה false positive, אבל הפאוור זה 1 מינוס בטא. זאת אומרת, מה זה false positive? false positive זה אומר, החלטתי אומגה 0, במצב אומגה 1. לא, זאת אומרת, דחיתי, לא סליחה, החלטתי אומגה 1 במצב אומגה 1. וכאן אתה צודק, יש כאן הנחה סמויה שהיכולת שלא החלטתי אומגה 0, החלטתי אומגה 1. כלומר שאני עשיתי החלטה, אני מחליט בסוף. ואני אמרתי לא, אבל יכול להיות גם מצב שאתה מתענד לנצח ביניהם.
וגם יכול להיות מצב שאתה... זה לא נכון שכל CI זר לכל DJ. ה-CN'ים ביניהם הם זרים, ה-DN'ים ביניהם זרים.
אתה לא יכול... לא, נכון. באין נתון זרים. אתה לא יכול גם להחליט כמה...
נכון. בין זרים, לא ברור לי ש-DN ו-CN...
אתה לא יכול לעשות גם את A וגם את B אחרי בדיוק אין צדים.
אחרי נכון, זה נכון. אבל יכול להיות שאתה חצית את A.
עכשיו אני הגדרתי את זה, זה בזילות. כלומר, לא אני הגדרתי, בוא נגדיר. שאתה לא חוצה לסף אף אחד מהספים קודם.
אוקיי.
כלומר, אתה לא יכול להיות שהיית ב-DN וגם ב-CJ.
אוקיי.
אם אין קטן מ-J.
אז במקרה הזה באמת הם...
אז הם באמת הם לא מכסים את הכל, אם אני מרשה מקרה שאני מזלת עליך. אז את הסט הזה, אני כרגע, אתה צודק שבמצאתי כאן, הנחתי שזה יש לו מזלת. זה צודק לגמרי, אבל חוץ
רגע,
מכיוון זה לא חכה מאוד אלגנטית, היא לא שלי, אני לא יכול יותר להתפאר בה. אבל זה...
הבנתי, בסדר. אתה דרשת בהגדרה של ה-DN ו-CN שאתה בין D ל-A כל הדרך. סבבה, שכנעת.
אם לא, אז שלח את הערות לבד עם אותך.
נשלח לבד?
אני גם חייבת
אוקיי.
לא, אבל זה הבנתי שאחד לא חוזר עוד. שאחד לא חוזר.
אוקיי, מישהו התחיל את רוטה.
כן?
לא יודע למה, אוקיי, בסדר.
שאחד פחות בטא, ובטא זה כמו ה-DN ויוצא לו אחד.
לא, בטא זה הסכום על CN
ואני לא מבינה למה זה אחד משנים.
לא
תהיתי כששמעתי את סוף התשובה
זה לא אחד משנים. אני אמרתי ככה, קודם כל CN הם אקסקלוסיב. האיחוד של ה-CN, האיחוד על ה-N של CN, איחוד על ה-N של DN, זה בעצם המאורע הכרעתי אומגה 0, וזה הכרעתי אומגה 0. זה הכרעתי אומגה 1, זה הכרעתי כאן אני אנחנו לא לגמרי עקביים עם הסיפור הזה. וזה מה שקראנו בקורס וגם בספר. עכשיו, הכרעתי אומגה 0, הכרעתי אומגה 1. עכשיו, ברור שאני לא יכול להכריע את שניהם במבחן הזה. לא יכול להיות מצב שאני אחצה את הסף, את אחד הספים, ואחר כך אחצה את הסף השני, כי ברגע שחציתי את אחד הספים החלטתי. אז לכן הדברים האלה, שני הסטים האלה גדולים. עכשיו, יכול להיות שהאיחוד שלהם הוא רק חלקי למרחב המובן שלי. כלומר, יכול להיות שיש משהו באומגה שהוא לא, זאת אומרת, לא הכרעתי אף פעם. זה לא יכול להיות ב-IAD. ב-IAD זה לא יכול להיות. ב-IAD אני יודע שהדברים האלה עולים לינארית. עולים לינארית, ולכן זה תמיד יחצה את עצמו. משהו מהלך מקרים בלי. באיזו שאלה מאוד יפה שעושים את עצמם כתרגיל מתקדם. אני חושב את ההסתברות של החצייה של הסף. אני מסתבר שזה כאילו האינדוסקאוט שם, זה מאוד חשוב בנור סייד.
לא יכול להיות שיש שתי אותיות, שיש להם את אותה הסתברות, ויש טקסט,
כן, זה לא יכול להיות, אם זה שכבר של A, רצף של A, אפשר להכניס להביא סופית, ניתן לזה קלקי, A אין אותה הסתברות. אבל נניח ל-A יש אותה הסתברות, גם בלי סופית, זה לא אומר שהסיכוי, אני רק טוען שהסיכוי לטקסט הזה הוא אפס. בסדרה אינסופית של A. אף אחד לא יכול לעשות. כי זה לא אנגלית, זה לא זו. לא, אני הנחתי שהטקסט נבע מאחד לסופות, כמו לאחד לסופות. אם זה IAD, כן. משולב לי או לא תוכחי, כמו משהו באמצע, אז באמת יכול להיות התנדנדים. אבל ב-IID, כמה אני יכול לזה שלום שלום, ב-IID זה לא יכול מצב מאוד חשוב. זה מאוד חשוב. עכשיו, שאלה מעניינת זה מה הכתוב, היי. אני אזרוק אותם, אם אני לא יוצא ב-12:46, אני לא אשם שהצמידו את שני השיעורים האלה.
אני יודעת, אמרתי לראות.
רבע שעה לא מספיק לך ארוחת צהריים.
שנה הבאה, שעה.
לא, זה לא יכול להיות.
שאנשים לקחו אותם בתור סינמה.
תכניסו את כולם כי אנחנו לא יודעים. So I just want one clarification following the questions in the break. So first of all, these two sets of sets, I mean the C's and the D's, usually disjoint even the C's and the D's. If, notice that we define them very carefully, that in the C's we cross the lower threshold exactly after n, and in the D's we cross the upper threshold exactly after n, and not before. During all the samples before n, I'm in between the thresholds. Okay? There was I assume that equal to the threshold has a probability. It's not really important, but it's not crossing the threshold. Okay? Yes. So we take a sample. Every sample belongs to one of the C's or one of the D's, or to this area which I call the gray area, where you never decide. But so it can happen that you never decide. I mean, somebody asked me, maybe you see a language of all A's, and you have to decide if it's English or French. Okay. I can't decide if it's English or French. The probability of such a sample to come from either English or French is 0, of infinite A's. Yeah. Or something, assuming that the probability of A is about the same in English and French. Okay. Now notice yes. No, it's a partitioning. Given the thresholds, given A and B, they are defined uniquely. I mean, and the likelihood. Once A and B are given, I can define the Cn and Dn exactly for any given A and B. Now, so the only thing I just want to mention that we actually showed last time that in the IID case, you surely decide at some n because it grows linearly, or decrease linearly. Actually, it's a very good exercise for those really advanced students here to actually calculate the probability of the threshold crossing time. So just again for those really students who needed to be challenged, we need to be challenged. Actually, there's a very famous paper, which is surprisingly due to Erwin Schrödinger, the famous physicist, from 1905. No, maybe 1915. Anyway, long time ago, before quantum mechanics, 1915, I think, which actually calculated this probability as a property of a random walk. And it turns out that the distribution of the crossing time is something, it has a distribution which is known as inverse Gaussian distribution, from very strange reason. It's not really inverse Gaussian in any statistical sense, but that's how it's called. It turns out recently, if you look at the neuroscience literature, this particular distribution is playing a very interesting role because it's precisely the probability that the neuron will fire after a certain amount of. So it's an interesting distribution. You'll see a lot of neuroscience papers mentioning inverse Gaussians. You can look at Wikipedia if you want. And this is precisely the distribution of the time that it takes to cross the threshold in this case, given the likelihood ratio or the KL. So it's a property of random walks. Okay, so this is all I wanted to say about sequential decision. It's for me this is a very important lesson because there are many new concepts that came out of this game, including this notion of online learning, that I can learn sequentially and make the decisions example after example. And notice that in the IID case, all I need to do is to update one number, which is the likelihood ratio, by multiplying it by a new one. So I can remember only one number, which is a sufficient statistic in this case for this decision. I don't then need to remember the sample. I don't need to remember anything else about the sample. That's all I need, is just to update this number. Okay, so now I want to start in the little time that we have, which is exactly 25 minutes, to start the next chapter in the book, if you want, which is called estimation or parameter estimation. So parameter estimation is a huge topic in statistics, which essentially has to do with inferring or inference of the parameter of a distribution from a sample. So in a sense, we have something which we call the parametric distributions. Which I don't want to try even to define it formally. But what we mean is that there is a random variable x, which can be anything. I mean, 0, 1, 1 to 6, reals, complex, Rn, whatever you want, categories, words, names, anything. But we usually assume it to be real, just for the case of simplicity, because this is what we usually do. Conditioned on some parameter. With theta, it can be a vector of parameters. Actually, both x and theta can be vectors in general. It belongs to some big theta, which is the parameter space. Okay, so this is usually, in most interesting cases, is some subset of our d of theta, where d of theta is the dimension of theta. So usually it's some real value. So for examples like this, I mean, so this is called the parametric distribution. And of course, essentially all the distributions we mentioned so far, maybe with the exception of English letters and French letters, which are also parametric, but they have a lot of parameters. So, for example, examples. Give me one. Out of the many that you mentioned so far, of a parametric distribution. Normal, okay, so normal. Normal, or what we call n mu sigma, let's say real one-dimensional normal. So usually what we mean by this is that there are two parameters. So theta is the sets of mu and sigma, where mu is anything in the real, and sigma is anything in the positive real. Okay. Usually we exclude 0, but it can be in some limit also 0. So this is a normal distribution. Okay. I don't know, a Poisson distribution, for example. You all know that? Poisson. So when we say that x is distributed normal, what it actually means is x is sampled from this density 1 over 2 pi sigma e to the minus x minus mu square over 2 sigma square, and I assume you all know that. Now, this is a density. It's not a probability, it's a density function. Another one, Bernoulli. Bernoulli. So when we say that x is say that M is distributed Bernoulli with some parameters n and theta, what we usually assume is that we are sampling, let's say, a coin flip. It has probability theta, theta and 1 minus theta, okay? And we ask what is the probability of having m heads in a sample of n size n. So this is actually the probability Pn of, so it has essentially two parameters that we think of. We usually don't think of n as a parameter of m, which is n over m, theta to the m, 1 minus theta to the n minus m. Okay? So it's again, it has a parameter theta, and it usually considered as a size, but you can think about it also as a parameter of the distribution. And this, we'll come back to this distribution, has many other important properties. Poisson, for example. You all know what the Poisson distribution is? It has what parameters? Lambda, yeah, the rate. Essentially one parameter. So what is the probability of having m successes in a Poisson process? Okay, so and so on. So essentially all the distributions, when you think about them, that we had so far, including, by the way, the multinomial distribution. What is the multinomial distribution? For example, the distribution of letters in English. So it's a histogram. Each letter has its own probability. The only thing we know about them, these are non-negative numbers in 0 and 1 that sum to 1. So I can think about each one of those n minus 1 numbers as parameters of the distribution. So it's a multinomial. What is the probability to see in a text of size 1,000 letters n1 A's, n2 B's, and so on? This is going to be a question I can ask. It's exactly an extension of the binomial distribution. Okay, we call the multinomial distribution. And we just replace it here by extend it to generalize multinomial. I'm sure you saw it. Okay? So it's a very simple extension. Okay, so there are many, many parametric distributions. Okay, so the problem of parameter estimation, in the little time that I have, so we can think about it. The problem, what is the problem? Estimate the parameter, or parameters, I call it parameter just theta, from a sample. A sample, usually, almost always at this point, we'll assume IID sample. It makes life a lot easier. But from a sample, it's really not part of the definition, but from a sample xn drawn from p to the n x given theta. So when I said p to the n, it's really the product. Okay? Now, I know the class. I know the type of distribution. I know it's normal. I don't know the parameters. Okay? So this is the problem. And usually we call this estimate, so the estimate is going to be some function of the sample, which has so essentially it's a sample, it's a function from the sample to what? To theta. So the space of parameters. Okay, so it's an estimate. This is what we call an estimate. Estimator. In Hebrew, we say it. We call it either עומד או משערך. תלוי אם אתה בא מהטכניון או ממקומות אחרים. You are jumping ahead, but it's all right. Yes, something like this. I want to cast this problem in the language of Bayesian decisions. Okay, so this is so this is the problem that statisticians call the parameter estimation problem. How do you estimate? What is a good estimate? Estimator. So I want someone to think about it in the notation that we developed for Bayesian decisions. So how do we do this? I really hate the boards in this class. It's terrible. But okay. So we can think about it as an action. Okay, this is some sort of a decision. I mean, it's an action that we have to make out of a sample. So again, we have the big picture that is so useful. We have theta. This is our world, in some sense. Well, I have to be careful here when I'm in my notations, but this is my. I think about theta as a random parameter that is selected, maybe with some prior distribution. Prior. You're going to see that this is going to cause us a lot of headache with prior. So at some point we'll try to ignore them, as statisticians usually do. But in our Bayesian formulation of the problem, we think about this as the world. So there's some prior distribution of theta. How is this theta selected randomly? Now, once this theta is selected, there is this something which we eventually going to call channel. How is the sample drawn from theta? So let's say I have a normal distribution. Let's say even I assume the variance is 1, but I don't know the mean. So I get a sample, size n. I independently sample the same distribution. Otherwise, it's not a good sample. The same distribution with the same mu. And then eventually, I'm going to estimate what mu is going to be. And you all can guess, I think, right now what it's going to be. So this is going to generate samples according to this distribution. And then we are going to make a decision or estimate the parameter. So actually, I have to tell you what I think is the best parameter. This is going to give us this estimate. So it's really the classical Bayesian decision problem. The only difference is that the state of the world is now become continuous and infinite dimensional. There are many possible values of the state of the world, and but we can still play exactly the same game. So in order to play the Bayesian decision game, what do I need? So I have already prior. I have the parametric family by definition. This is the way the world affects, the parameters in this case affect the samples. And I need one more thing in order to make a decision. I need a cost. Okay. So there should be a cost function. Lambda, or if you remember this function, which in this case is it's usually a function of what? Of the action and the state of the world. In my case, the action is the estimate. Okay? Or the estimator, so it's a function of theta hat, given the state of the world theta, in my notation. In most places don't put a given here, put just a comma, but it's all right. No, well, maybe. So there are many choices of these functions. Okay, as you said, as Karen said, so we can have many different choices for the cost function, and each one of them will give us a different type of estimator. So this is the game we want to play in the next 10 minutes. So for example, and of course, once we have the cost function, the base optimal decision is going to tell us what to do. Take the one which minimizes the conditional risk, where the risk was the expectation of the cost over the state of the world, given the sample. So again, we are going to have a conditional risk of the estimator given the sample, which is just the expectation of a theta of the estimator. I'm sorry, of lambda. Lambda given theta hat and theta times p of theta given the sample. This is what we have to do. Okay. Is this clear? It's not written clearly, that's for sure. So base optimal estimator is the general procedure take theta hat to be the arg mean over all possible choices of theta hat. Let's call it theta star to be more precise. Over all possible choices of theta hat of the expectation of the conditional of this expectation of over p theta given xn of lambda theta hat theta. So this is what base optimal is telling us. This is just a reminder. Just translate it to our problem. And of course, what we need in order to do this expectation of a theta is we need the Bayes rule. Okay. So p of theta over xn is what? That's where we need the prior. So it's p of it's the prior of a theta times the likelihood or the probability of the sample given theta divided by this normalization, which we call the probability over the data. So this is actually an integral over all thetas with the prior and everything. The thing that makes it normalized. Okay. This is what Bayes rule is telling us. My high school math teacher was willing to kill me if the equality was not exactly where the fraction line is. So I have really something rooted in me about it. Okay. So well, let's start. I mean, we really have little time, but Noga will say much more about it tomorrow. So the first natural choice of a cost function, as Karen already almost said. So the most popular estimator in engineering applications and in many other cases. So what we want theta to be close to theta hat. That's the idea. So we want to penalize somehow the cost function should be large if theta hat is not close to theta. Okay, so the first choice is what we call minimum square error, or MSE. This is such a common name that I think you should know it, MSE, or minimum square error. And in this case, or minimum square error estimate. I don't know exactly what it says. Maybe the estimate, not the error. But minimum square error, or minimum square error estimate, which is taking lambda theta hat given theta as simply the square error, theta hat minus theta squared. Okay, in general, we talk about multidimensional, so allow me to write it like this. The norm L2 square. So sometimes it's called an L2 error. Okay? So this is just called what we call the norm. So it's a vector. So what is the L2 norm of a vector? Sum of the squares, square root usually, if you want to talk about the length. Okay. So this is minimum square error. Before I show you what happens there, what types of errors, or other types of error you can think of. For example, L1 error. Why not? Just so L1 is lambda. Call it MSE. Let's call this L1, which is simply the absolute value. Okay. So again, the norm L1, but in the one-dimensional case, it's simply the absolute value. In general, it's the L1 norm. I don't want to define it. Okay? This is also a good measure, a different measure. It's penalizing me slightly less harshly than L squared. Okay? There's actually something which is even more extreme. I want to penalize anything which is not theta, the right theta. Remember, this was exactly, we had an error like this in the discrete case, 1 minus delta ij. So there's another one which I'm going to use, which is anything which is not theta is bad. Okay? So since we're talking about continuous function, this is, sometimes you can call it the infinity norm or something like this. but it's actually lambda. Let's call it. You're going to see that this is going to give us an estimate, which you call the maximum a posteriori. And in this case, I write it in a way which I need to explain. I hope not to all of you, but this is actually the Dirac delta function. So you remember it was 1 minus delta ij for the discrete case, but delta ij was the Kronecker delta. You all know what this is. Here now I'm talking about continuous variables. So this is a very ill-posed function. Never think about all of you. How many of you haven't seen delta function, the Dirac delta, anywhere? Good. Okay. So I don't know if when you learned about Dirac delta, whether it was physics or anywhere else. I'm going to turn black out of here. This type of function, which I don't even want to try to define right now, has a meaning only inside an integral. Never think about delta function outside of an integral. And essentially, because you're talking about ill-posed quantities. But what do you mean by it? So it's really what it means that if I integrate over delta, I get the value of the integrand at the point where delta, the argument of delta is 0. So sometimes we call it point sampling. So this is essentially, delta function is defined such that for any function in some reasonably defined space, integrated, this is f of 0. This is the way I think about it. So it's really sampling the function at the point which is the argument, at which the argument of delta is 0. Okay? So that's a definition, if you want. That's what I mean by delta. So in this case, it means that it's going to be infinite. It's going to be infinite in some sense, whenever theta prime is not theta. But it doesn't make sense without this integration. So for example, the integral of delta itself is 1. Yeah. Okay? Dirac delta. Well, we have to honor some people, so Dirac delta function. He introduced it for the physicists very intuitively, long time before the mathematicians accepted the existence of this thing. But it happened eventually. So we call it a Dirac delta function. It's a very natural thing to do. It's a function that samples another function at the point. Okay. So I'm going to talk about these and maybe other types of estimator, but these are the main things. So let's take just in the next 5 minutes and see what is the L2 estimator. Okay, so what the Bayes optimal procedure tells me: write the expected risk and take the minimum. So what is the expected risk? So the risk of the minimum square error MSE of theta hat given a sample is what? Is the expectation, let's write it as an integral, I hope you're not worried too much, of what? Of the cost function. So it's theta hat minus theta square. We do it in 1 dimension now, that's to make things a little easier. You can generalize it very easily. So it's theta minus theta square times the probability of theta given the sample, and what I integrate is over theta. So assume that everything can be extended to n dimensions. It doesn't really matter. Okay, so now I want to find the minimum. How do I find the minimum? So this is the square error. Okay, so this is going to be some function of the sample eventually. I want to select the one which minimizes this risk. This is what I mean by argmin. Okay? So how do I find it? XOR. We take the derivative and turn it into 0. Okay, so this has a minimum. Maybe you don't see it immediately, but it has a minimum. I don't have to. It's very easy to convince yourself that the parabola has a minimum. So essentially, this I really don't have to worry too much. I simply take the derivative with respect to theta hat of this risk of this. I don't have the time to write it. Okay, but what is it? So the only place in this integral that depends on theta hat is square. So I assume that that the boundaries don't depend on theta hat, and I assume that nothing else is there. So how do you take the derivative of a square? I know it's the end of the lecture, so it's a very hard question just to make sure that you are awake. Okay. So the derivative is simply 2 times the integral of theta hat minus theta, the same probability. Nothing else depends on theta hat, okay? Very simple. But this should be equal to 0, because I want the minimum. Okay, so from that you see immediately, I really don't want to erase this. It's important. But so from that, it's a trivial. So the integral of theta hat over p of theta doesn't really matter because theta hat doesn't appear there. So it's simply 1. And I get from that the theta MSE of the sample is what? Is the integral of theta over p theta given xn dxn. And this is something which it's something which we, sorry? D theta, yeah, sorry. D theta, xn is given. Yeah. The sample is given. So that's why it's a function of the sample. And this is something we call the conditional mean or conditional expectation. איזה חצי? Can erase this too. Okay, okay, this is the conditional expectation. So essentially, it tells something very intuitive. The best least square estimation is the mean, the posterior mean, or posterior mean, if you want. Mean of theta. So given the sample, calculate the probability using base over theta, and then take the mean of this. Okay, I don't have the time to show you even one example, but I'm trust Noga to do it right at